Okay, so welcome back everybody for this afternoon session. And the first speaker is Nick Higham from the University of Manchester. He's going to talk about numerical stability of algorithms at extreme scale and low precisions.
Thank you very much, Martin. It's a real pleasure to be speaking at the International Congress of Mathematicians. Let me say straight away that if you'd like to get the slides, there is a link there to them. So this talk really is about the limits of what we can compute, looking to the future as problem dimensions increase. So I assume I've got an n by n matrix problem, where the algorithm would be exact in exact arithmetic. So the only errors are rounding errors. Most algorithms have a bound of the form some function of the dimension times the unit round off. And unit round off is a measure of the accuracy of the arithmetic. It's about 10 to the 16 for double precision. So the issue is that the problem dimension is increasing as time goes on, as computers get bigger and faster. And we're in an increasingly mixed precision world where we not only have double, but also single, half, and even quarter precision nowadays. So the unit round off is also getting larger. And so our error bounds are getting larger. And so what does this mean about what we can compute in the future? That's really the question I want to address. And let's have a look at the world's fastest machine, Frontier. The top 500 list is produced twice a year, and it ranks the world's fastest supercomputers. And there's a new entry last month, Frontier at Oak Ridge National Laboratory, made from AMD processors and GPUs. And it's able to achieve 1.1 exaflops when solving a linear system of equations. So it's the world's first exascale machine. Quite a big landmark in high performance computing. It also has half precision as well as double. And the HPL AI benchmark uses half precision as well as double and was able to solve a system of a similar size about 7 times faster. I put exaflops in quotes because most of those flops are actually half precision flops. So that's a pretty large system. How is n growing as time goes on? Here's some data from the database. And you can see that, roughly speaking, every 10 years, we get a factor 10 increase in the dimension of the systems the largest computers are solving. So in 100 years, we'll be up to 10 to the 17, and we won't be able to guarantee anything about the accuracy of computer solutions in double precision if we just use the usual worst case error bounds. There's a bit more detail on the arithmetics. The two at the bottom we've had for many years. Half, FP16 is the IEEE format from 2008. Google have their own version of half called bfloat. And early this year, NVIDIA introduced the quarter precision on the Hopper 100 GPU, which has a very, very low or very large unit round off. So many precisions available on today's hardware. If we look at the error bounds, this is the standard Wilkinson result for solving n systems in n equations in n unknowns, written in modern notation. So Wilkinson showed that the computed solution is the exact solution to a perturbed system, where the perturbation delta A is bounded as indicated. So what's the mod of the matrix? It means you take the elements, the mod component-wise, and inequalities hold between corresponding elements of the matrix. So the constant here is gamma 3n, and I'll show you at the top there the definition of gamma. So it's basically, gamma n is basically nu plus higher order terms. I'll assume that the L and U here are of modest size. So basically we've got 3nu, or if you like, just say nu. And so for today's largest systems, the error bound is of order 1 for single precision and 10 to the minus 9 for double. So we can't really solve, according to this analysis, and today's largest systems in single precision. Well, can we optimize the bounds a bit? If you look at the proof, then in the midst of the proof, you have this inequality, where the little circle here is the Hadamard product. It means you take you multiply these matrices component-wise. And the thing to notice at the top left, we have constants of order 1, increasing down the diagonal, and we still have a gamma n at the bottom. So although it's smaller at the top, we still have an NU somewhere, so it doesn't really help to try and use that matrix inequality. That's not very fruitful. Let me say a bit about deep learning. About 7 years ago, half precision started to be used in deep learning, and this paper by Cole, Barrio, Benji, and David was one of the first that did it. They were training and running trained networks in half precision. Jeffrey Dean from Google notes that deep learning models are very tolerant of reduced precision. If we look at the inner product of two vectors, deep learning mainly is doing matrix multiplication, which involves inner products. So if we look at the error bound for an inner product, we have a constant NU, and this is of order 1, even for quite small n when you're dealing with half precision. And in deep learning, they're certainly using dimensions bigger than 2000. So the standard error analysis doesn't even guarantee the correct sign for these computations. And this is a bit worrying. So here's the partial explanation that I'll elaborate on in the rest of the talk. So inner products are not computed in the obvious way. They're computed in a blocked way that actually reduces the error bounds. The bigger algorithms that we use that are built in inner products are also blocked, and that introduces further reductions in the error constants. There are some hardware features that benefit us automatically without having to do anything at all. That's really good news. And if you take a probabilistic approach to the analysis instead of a worst case approach, you can also do a lot better in terms of the error bounds. So I'll cover these different topics in the rest of the lecture. Now, one thing worth saying is that blocking is done for speed. So blocking of algorithms is done purely for speed normally, and it's really a side effect that it gives a benefit in accuracy, a very welcome side effect. And even hardware features I'm going to mention are done for speed, and we just happen to benefit from the accuracy as well. So this is rather fortuitous, perhaps. So let's look at a blocked inner product. Two vectors x and y, sum xi yi. There's the usual worst case error bound. But I'm going to break the vectors into two pieces. I'm assuming n is 2b. So first of all, I compute the inner product of the first b components separately. I compute the inner product of the last b, and then I just add them together. And I claim that reduces the error bound by about a factor 2. So why is that? Well, think about it from the point of view of x1, y1. And most of the operations here are additions, so we'll ignore the multiplication. So x1, y1 gets x2, y2 added to it, then x3, y3, and all the way to xn, yn. So it participates in n-1 additions, giving it an error bound proportional to n, nu. But in the block form, x1, y1 only has b-1 additions, plus another one here. So n becomes essentially b. And b is 2. So this leads to this reduction by a factor 2 here, by the blocking it into two pieces. We're halving the number of additions that x1, y1 undergoes. Well, if you've done that for two pieces, why not do it for k pieces? So if n is kb, we can break it into little k by k or k by 1 subvectors, do those k pieces, and just add the pieces together at the end. And a similar argument gives you an error bound where n has become n over k now. What's the optimal k? Well, if you optimize over k, k's root n would minimize the bound. And so n would become root n, which is a nice improvement. That's not very practical. We can't, in practice, take block sizes that depend on n. We normally take a fixed block size like 128, 256, something like that. But blocking is a very simple idea that automatically reduces the error bounds and also gives you speed benefits because to do with the cache and modern architecture structures. There's more we can do, so let's focus on summation and think about summation now. The obvious summation algorithm, where I just add the components in the obvious way, is called recursive summation. Okay, and we can think about reorganizing this computation. So that there is a standard way of doing this, which is what I've just been describing. You break x and y into pieces, and you just sum little pieces, and then sum the partial sums. So sum blocks of size b, and then sum the partial sums. Okay, obvious approach that again is done for speed in practice. Now, think of B as, say, 256 and n as being very large. You can see that most of the work is in step 1, because I've got just n over b here, and I've got n minus n over b here. So most of the work is in step 1. So an idea is, we don't have to use the same method in step 1 or step 2. We could use a more accurate method in step 2. It'll be more expensive, but it won't necessarily affect the overall cost very much, and it might improve the accuracy. So let's try that idea. This is work with Pierre Blanchard and Theorem. So we assume we have two summation algorithms, one called FAStsum, that's fast, one called accurate sum, that's accurate. And we compute the, these little partial sums with the fast method, and most of the work is done there. And then at the end, we just compute the sums of the partial sums with the accurate method, accurate sum. So FAStsum is doing most of the work, accurate sum is just doing n over b additions. So the question is, does that actually benefit accuracy at all? So it's easy to analyze. I'm assuming that the fast method has this backward error result here at the top. So the fast method computes the sum of some slightly perturbed data where the perturbations are bounded by epsilon f. And for the accurate sum, it's bounded by epsilon a. And a very simple bit of analysis gives you this result here. So the backward errors for the whole algorithm have the term epsilon fb plus epsilon a n over b. Now, the accurate method can be chosen to have errors of order u with no n dependence. And so this n over b actually will disappear to first order, and we can be left with a first order term of order the block size. So what might I take for the accurate method? I could take recursive summation at twice the working precision. So do it in quad precision, for example, if I'm working in double. Or there's a method called compensated summation, which goes back to the 1960s due to Higham, Moller, and others. And it's a rather clever method. When you do an addition in a sum, you immediately estimate the error in that addition, and you add it back in on the next step. It's a rather weird algorithm. It roughly doubles the cost, but it turns out it gives you a very accurate solution. So if I assume that we're using that method, compensated summation, for the accurate method, recursive for the main method, for the fast summation, the overall error bound has first order term that's independent of n, and n only appears in the second order term. So as long as n is not extremely large, the second order term will not dominate and will have a nice constant error bound independent of n. And recall that for block summation, it's n over b. We've got that down to just b plus 1 now. So that's a significant improvement, hopefully at the cost of not too much extra computation. I'll just show you one example to illustrate how it works. This is summing random uniform numbers from the 0-1 interval. Block size 128, single precision. And at the top here, so I'm plotting the backward errors on the y-axis, the problem size on the x-axis. And the recursive summation gives you this curve at the top. Blocked summation, done for speed, gives you certainly a benefit in accuracy. If you were to do the expensive compensated summation, you would get a yellow curve that hides behind the purple curve here, doing much better than these two. And the FABsum method that we just described is the purple curve, which largely overlays compensated summation. And it's a little bit worse to start with because the block size is still quite big relative to n. If we decrease the block size for those smaller n, we'd do much better. And experiments show that you don't actually have much of an overhead in terms of cost for FABsum. So that really is a nice benefit from blocking both accuracy while having very little effect on the speed of the computation. Once you've got summation and inner products, you can do matrix multiplication. And here is a blocked matrix multiply algorithm, which is really just the obvious thing. If we assume that A is n by n and n is a multiple of b, we just break everything into little b by b blocks and write down the usual formulae blockwise for matrix multiplication. And this is written in the form of a loop. There's only one thing to emphasize, and it's rather important here. So those of you who are programmers will be looking at lines 5 and 6 and saying, what's the point of this variable x? I could just combine those lines into one line that says Cij is Cij plus Aik times Bkj. Why do I need the temporary variable x? The reason is the algorithm is ambiguous otherwise. It's important that you compute x and then add it to Cij, and that you don't do it by starting with C, well here it's CRS, and then gradually adding these A's and B's. And this is for the same reason when I talked about inner products. X1, Y1 must not have added to it all the subsequent terms. You really need to do things in a genuine block sense. So that's a bit of a pitfall if you're programming this. If you tried to get rid of X there, you could end up not having the right block algorithm, and you'd lose the accuracy benefits. EPYC is the state-of-the-art software for linear equation solvers and eigenvalue and singular value problem solvers. And all its algorithms are blocked with block sizes 128, 256. And so it automatically gets reductions in error bounds by a factor B or so. And there's actually a further benefit because EPYC calls low-level routines that the manufacturers provide, and those themselves might include blocking. So there's two levels of blocking, and it's two levels in which you can benefit from reductions in error bounds. Now, if you look at the EPYC manual, you'll see that error bounds are always stated in terms of P of n, and no mention of the block size. So why doesn't EPYC mention that the block size, the block algorithm, gives you a small error constant? I think there are several reasons. Wilkinson, back in the 60s, when n was only 100 or so, that was a large problem, said we're not really trying to optimize constants, we're trying to understand the behavior of algorithms. What makes them stable, what makes them unstable? A lot of people have followed that advice. Also, the constants do depend on the particular block algorithm. So the difficulty is that when you state a result, it might only apply to one particular block algorithm, it might need tweaking for another block algorithm. And also the analysis is more complicated at the block level. So I think those are reasons why you will not tend to find mention of this effect of the block size, but it is very important. And one of the key messages of my talk is that we should make it more clear that we're benefiting from blocking, and that's giving us big improvements in the error bounds. Onto the hardware. Here are some reasons why we get benefits from hardware. So most of us have Intel chips on our computers. And since the 1990s, Intel processors have had 80-bit registers internally. And the compiler, when working in double precision, may use those wider registers for intermediate computations and storing intermediate results. So we might think we're working at 64-bit accuracy level, but we might be working at 80-bit level. And it's all hidden by the compiler. And the unit round-offs for these two precisions differ by a factor 2048. So in the very best case, you might be getting an error about 2,000 smaller than you expected by virtue of those registers being used, which is all good news. There can be problems with something called double rounding, which for the vast majority of people is not an issue at all. But if you really want to get into the details, that's one slight disadvantage of using these registers. But overall, that's very good news, just that it's hard to know when that's happening in the background. The second thing that benefits us is something that's quite, well, more and more widely available, the fuse to multiply add operation. First appeared in probably the late 1990s, now quite widely available. There's a hardware instruction to do x plus y times z, an add and a multiply in one instruction. And this is done for speed, and it's the same cost as doing a separate add and multiply. To be more precise, this is actually a pipelined operation. So when you're doing a lot of these things, when you have a full pipeline, the computer will deliver one result per clock cycle. So this is designed purely for speed. But it turns out you only get one rounding error. So the normal error bound would be this one here. There's a rounding error for the multiply, there's a rounding error for the add. With an FMA, there's only one rounding error overall. So all our error bounds get reduced by a factor 2 automatically if they use an FMA. So that's very nice. That's a free of charge benefit from an FMA. Again, there are some situations where FMAs can be a bit problematic, but for most people, that's not, the intricacies of that are not really something you need to worry about. More modern hardware, GPUs in particular, now include matrix versions of FMAs, matrix multiply versions. So these are little matrix multipliers, C plus A times B. And normally you provide A and B in low precision. The computation is done at a higher precision, and you get back the answer, C plus A times B, at the higher precision. So this is done very, very fast on a GPU with special purpose hardware. So essentially the computation is computing the inner product of these two lower precision matrices at a higher precision, adding it to C, and doing that all in high. And the beauty of this operation is the output D can be fed back into another FMA as the C. So you can have a chain of these things where you just keep computing these long chains of matrix multipliers, and that's what enables you to implement a general matrix multiply of an arbitrary dimension. What sort of hardware is available? Well, here's a partial summary of some hardware. So Google, their tensor processing units have always had quite large FMAs, doing matrix multipliers of order 128. Other manufacturers tend to be quite small, sometimes rectangular matrix multipliers, like 2x4 times 4x2, and a bewildering variety of possibilities nowadays for the two different precisions with which these things work. So this is really getting quite complicated to understand, and they're not always very well documented by the manufacturers as to what's going on inside. But they're very, very fast. So if you really want to get your machine to run as fast as possible, you want to be trying to exploit a block FMA, if at all possible. I should say they're also usually not fully IEEE compliant, not fully compliant with the IEEE standard for floating point. So that can give some strange effects like non-monotonicity of rounding. We did some error analysis of this a couple of years ago, before the very latest machines became available. Fortunately, we decided to parameterize things, so the analysis does apply to all the current hardware. And we did the analysis for a general matrix multiplication, AB. And the error bound has a constant in it. And I'm just simplifying things now to show you this here. So if you did the whole thing at low precision, you would have an error bound whose first order term is essentially n times the unit rounded for the low precision. So think of low as 10 to the minus 4. If you did the whole thing in high precision, let's say 10 to the minus 8, single, you'd have an error bound n times 10 to the minus 8. With the block FMA, here's the error bound. And I guess the main point to note is that for large n, you're doing about as well as if you did the whole thing at high precision in the usual way, because this term will be dominant for large n. And yet this is done very fast and only by inputting low precision data. So it's quite remarkable the way these things work. And you can do the analysis also for LU factorization for solving linear systems. How does this work in practice? We did an experiment on the NVIDIA V100, which is probably, I guess, 3 or 4 years old now. We have matrix entries, random uniform numbers from 0 to 10 to the minus 2. We're computing relative errors on the y-axis, and the x-axis is the problem dimension. So if you do the whole thing with the tensor cores half precision, without, so with the GPU's half precision without using the tensor core, then you get this line here for the errors. Errors are about 10 to the minus 3 and above. Doing the whole thing in single, again, without using the tensor cores, you get the blue error curve. Using the tensor cores, you get the red. So it's in between. Okay, so it's in between doing everything in half and everything in double, but it's much faster than the double. It's about this computation is about 7 times faster than the blue curve there. So those tensor cores really are highly optimized, and it does pay to take advantage of them. As long as you know what you're getting in terms of accuracy, it's well worth exploiting them. So the final part of the talk is about probabilistic error analysis. And I like this quote from Pete Stewart, who says that to be realistic, we must prune away the unlikely. And so we must necessarily have a probabilistic statement. When I talk about worst case bounds, I'm assuming that every rounding error has its worst possible sign and magnitude. And of course, typically when there are millions of rounding errors, that's very unlikely that that would ever be inequality. So Peter's saying, try and get rid of all those unlikely cases and come up with some probabilistic statement. Wilkinson had already thought about this in the 1960s when he said in his book, the statistical distribution of rounding errors will reduce the function of n occurring in the relative errors, in the error bounds. And we should be able to take the square root of that constant. So he's saying if you had an error bound n times unit round off, then it's more like root n times unit round off, probabilistically or statistically. And a lot of people over the years have regarded that as a rule of thumb, but it's never been proved. I've never seen any attempt to make that rigorous. I think the argument is based on the central limit theorem, but there are three problems with that. First of all, the central limit theorem requires independence of the random variables, so the rounding errors have to be independent and mean zero, and they're not always independent. So we'd like to have a weaker assumption than that. This argument requires you apply the central limit theorem to the first order part of the error. And so you don't really know what's happening with the higher order terms. And of course, the central limit theorem, as far as I'm aware, never tells you how big n has to be, just says for sufficiently large n. And so, does that mean n is 1,000, 10 to the 5, 10 to the 10? In my case, it's hard to know. So we took another look at this, and I'll describe the approach that we've taken. First of all, let me just say what is the usual way of doing the worst case analysis. So this is a little theorem or lemma that I use all the time. So we have these rounding error terms delta I. They're bounded in magnitude by the unit round off. N is less than 1. And the product of 1 plus delta differs from 1 by at most theta. And theta is bounded by gamma n, the quantity I had earlier. So it's just saying how much the product of 1 plus rounding error terms, how much it can differ from 1. What's the worst case? And the bound is proportional to n times unit round off. So it's really the basis of most rounding error analyses in some form or other. Some of them are like this. So what we would like is a probabilistic version of this result with hopefully a smaller bound on theta, making some assumptions on the delta i's. So what I'll assume is, first of all, same model as before in terms of the every operation having a rounding error bounded by unit round off, but the new part is the mean independence. So the delta i's are assumed to be random variables of mean 0 and the mean independent. And mean independence is this condition here in terms of the expectation. And so this is weaker than independence. Independence implies mean independence. Notice the delta i's don't even have to be from the same distribution. They could be from different distributions. So what we're able to show is an analog of the little result I had a moment ago, where under that model, the error bound is now not gamma n, but gamma n tilde. I won't give the explicit formula for gamma n tilde. We have it in terms of an exponential, but it's basically root nu. Now in this result, you have to choose lambda. So lambda is a constant that comes up in the analysis. So you choose a lambda and you get that result. So lambda appears in the bound and it appears in the probability. So this result holds with the probability at least this, and there's an exponential decay here. So the proof is based on martingales. It works for all n. Bounds valid to all orders. Now, about the probabilities, we've extended this to various algorithms, and in every case, I think if you take lambda is 12, and the largest n today is 10 to the 7, then that probability is always within 10 to the minus 7 of 1. So we have a modest lambda, the probability is essentially 1 in practical terms from my point of view. So that's nice. So what we want to do is use that to try and get some probabilistic bounds for our different algorithms, inner products, LU factorization, and so on. Here's what we can show for inner products, 2 vectors x and y. The computed inner product has a backward error delta x, which I put the backward error on x, I could have put it on y. And this is a component wise inequality again. Absolute value means take absolute values component wise. So it's basically lambda root nu mod x. The worst case bound is just n times u. So at the n has gone to a root n, a significant improvement. For linear systems, well, once you've got the inner products, it's actually quite easy to go to linear systems, because linear systems, early factorization, triangle solves can be expressed in terms of inner products. So it's not hard to get this result here. The backward error for solving x equals b has a bound that's essentially, I guess, 3 gamma tilde. So this is like 3 root nu plus higher order terms. And there's a bit more in the probability, but this is still included in the comment I made earlier about being very, very close to 1 for modest lambda. And how does this compare with practical experiment? There's a collection of matrices called sweet sparse, but Tim Davis in the US has maintained for many years. These are sparse matrices from real life, often engineering applications. And what we've done is take 943 of these matrices. We've plotted the backward errors on the y-axis, the problem size, the size of the matrices on the x-axis. So each little square is just a matrix from his collection, but the matrices have no collection with each other necessarily. So these are the actual backward errors. The worst case bound is the blue, and the probabilistic bound is the red. And so you see there's a significant benefit from probabilistic approach, assuming that the rounding errors satisfy the model that I've got. I'll say a bit more about that in a moment. Now, we've been talking about inner product-based operations so far. Orthogonalization, QR factorization, this doesn't extend immediately to that, because in QR factorization, you have other operations. You have vector scaling, vector addition. It is not trivial to extend these results to QR factorization, but we have been able to do so. And so here's a similar result for QR factorization. So under the same model as before, and a certain technical assumption I won't go into, this is very similar to the standard result, the standard worst case bound. Now this is a bit unusual. So the R hat here is the computed R hat, but I'm saying there exists some exactly orthogonal matrix Q. And that might seem a bit odd if you've not seen this result before, but there isn't a unique Q hat. In fact, we don't normally even compute Q in many situations. So the result says there is an orthogonal Q that satisfies this condition, and column-wise, the norms of the backward errors are bounded in this way. And the important thing is it's root mn when it's nn for the worst case bound. So again, I've got the square root of the dimension-dependent terms. And this is proved using a matrix concentration inequality by Joel Trop. Interestingly, the same applies to Gibbons QR, which is a very different algorithm. And that also gets its constant square rooted. And so once you've got this, you can then go on to apply it to all kinds of algorithms that use QR factorization, like the QR algorithm for eigenvalues, SVD, and so on. So I can now say that most of the algorithms in numerical algebra are now covered by this probabilistic error analysis approach. Now, I've not said anything about whether the model is valid, and there's a lot I could say, but I haven't really got time. But I'll just describe one situation where the model, I'm assuming, is valid. And this is for stochastic rounding, which you probably haven't heard of. But it goes back to Forsythe in 1950. So imagine that, and this is the real line, these are two adjacent machine numbers A and B. In some computation, I've ended up with X, and I now need to round it back to a machine number, to either A or B. Normally, we'd round to B, because that's the nearest of the two machine numbers. That's called round to nearest. It's what almost everybody does all the time. It's the default in the IEEE standard. But what stochastic rounding does, it says, well, let's not do that. Let's randomly round to A or B with a probability that depends on the distance to A and B. So in this case, I'm closer to B than A, so I'm more likely to round to B than A. Okay, so there's an obvious formula for just the proportion of the way I am along between A and B. So there's always a slight probability that you'll round to the further away number. And it turns out that with this rounding mode, the rounding errors are mean zero and mean independent. Okay. So the model is always true for stochastic rounding, interestingly. And there's been a lot of interest in stochastic rounding in recent years from the machine learning community particularly. I'll give you one example. So it always satisfies the assumptions, and so yeah, we can unconditionally replace nu by root nu in the worst case bounds. Let me show you one example. So this is for the harmonic sum. So I'm summing 1 over k from k is 1 to n in half precision arithmetic. This accuracy about 10 to the minus 4. And if I do it in the obvious way with round to nearest, I get this, these blue circles. With stochastic rounding, well, now the result depends on the particular run because the rounding is random. So the whole range of stochastic rounding is shown in pink, and there's a particular instance of stochastic rounding. But clearly, stochastic rounding is doing much better, giving much smaller errors than round to nearest. This is an example where you get stagnation. Stagnation is when you're adding a very small number to a partial sum, and what you're adding is so small that it can't change the partial sum. And so the rounding error is therefore negative, and it's negative, negative, and negative for the rest of the computation, and the model then is not satisfied. You haven't got mean zero rounding errors. And stagnation happens in machine learning. This is what the machine learners have realized. And that's why they like to use stochastic rounding now, at least in some situations. Okay, so stochastic rounding, nice idea. It's not widely supported in hardware. There is some hardware that supports it, but we may see more of that coming along in the future. One other thing I want to mention briefly is random data. We talked about random rounding errors, but what if the data itself is random? So let me make an assumption here. Some of the data di is independent random variables mean mu x and all bounded by epsilon d, and the mean independence now includes the data as well as the rounding errors. So that's the modified model m dash. And what motivated us to do this was people often, as we've done, use random data in tests. I used random uniform in the 2 experiments I showed you earlier. So the data was random there. And what we've noticed over the years is that with random data, you often get much smaller errors than the analysis suggests. So we were trying to understand why that was. And here's a result that I think gives some insight. So under that model, with random data and random rounding errors, you get an error bound that has an n to the 3 over 2 and an n. And notice the n to the 3 over 2 is pre-multiplied by the mean of the A data and the mean of the B data. So if mu A or mu B is 0, then the n to the 3 over 2 disappears, and you're left with something proportional to n, which is growing much more slowly. So this, I think, explains why, and we found this in our own experiments. When you have random data centered on the origin, rather than say 0, 1 uniform data, you often get much smaller errors. This is the reason this bound has this term that just disappears, the faster growing term there. So putting everything together, block algorithms are giving us a reduction in error bound by a factor of the block size. It's often blocking at multiple levels, so we can get different blocking benefits from hierarchical blocking. Hardware gives us some automatic error boosts. And if, for example, you had block size 256 and you're using 8-bit registers, then potentially you could be getting quite a large boost in accuracy if you multiply these two things together. The probabilistic error analysis gives you the root n that Wilkinson predicted all those years ago, which we've now made that rigorous. And what's nice is that if you apply the probabilistic analysis to the block algorithms, then it goes through. So originally we had b plus n over b for a block tenor product. Probabilistically, it becomes root b plus root n over b. So you get the square rooting and block size effect combining nicely there. So final points. The classical analysis can no longer guarantee that many of the computations we do are giving any accuracy at all. And so we have to look more carefully at what's going on. Blocking was definitely introduced for speed, as were the hardware features, but they are boosting accuracy. Even if you don't realize it, you're getting a real boost in accuracy from these features. And the probabilistic approach, these assumptions are often valid, is giving you the square rooting effect for the error constant. So I'm not claiming that this explains everything. There's certainly, even with all these things together, there's still, often the results are even better than even all these things predict. So I think we're always going to need new analysis. We need to keep a close eye on the development of the hardware, because who knows what will come along in the future. Top 500 like machines, future GPUs, in terms of the clever things they do for speed that may or may not improve or may actually make worse the accuracy. So we need to keep a close eye on that and analyze it and understand what's going on. Thank you. I'll stop there.
Thank you very much. I think we have time for a few questions. If you may. Just maybe wait for the microphone.
Yeah. Hi, Nick. According to you, it's really nice work. If I have a particular computation, numerical computation to do, is it possible to use machine learning or some mechanics find out the distribution of these rounding errors or the correlations?
So can you find out the distribution of the rounding errors? Quick answer is I don't know. I think we have thought about that a little bit. One of my students looked into that, I remember. It's hard to know what the, given their numbers, what distribution are they from? If you have any ideas, I'd love to know, because it would be nice to test, the hypotheses. At the moment, we've been focusing on proving, like for stochastic rounding, that the assumptions are true. Testing whether they're true is difficult because of the curse of dimensionality as well. You need a very large n to be able to try and check if you've got the right, I think, to check you've got the right distribution.
Any other questions? I think I had a question regarding the stochastic rounding, which is of course very appealing for probabilists. You said that there's some hardware that actually implements that. So I was kind of wondering how that works, because it would need a sort of, very high frequency stream of random bits.
Yeah.
It seems very costly.
It's very specialized hardware. Is it GraphCore, who make chips for machine learning? I think have some hardware. There's random numbers, and there's the sort of getting an accurate answer to be able to know where you are on the interval. Those two things combined. We have a survey paper on this published in early this year, and one of my colleagues is a real expert on computer arithmetic, so he does go into some detail on that. But yeah, it's tricky, and at the moment it's only on this very special purpose hardware, nothing like on desktop Intel processors and so on. And it's not clear if it will ever make its way there. But even doing it in software, I guess that's what the machine learning people are often doing, and they're still finding it helpful there.
So let's thank Nick again.
So Nick, thank you very much. I understand from the green room assistant that I am to say a few words at the conclusion of this talk. You all will have to excuse me. This format is completely new to me for an ICM. But Nick, I found your talk wonderfully illuminating. I had not been aware of the advances in hardware and the concomitant advances that would necessitate in analyzing error bounds and examining the rounding errors. So thank you very much. That was a wonderfully informative talk. Our next talk should begin shortly. And yeah, I hope everyone